will not be comprehensive. So our final, so for the first, let me see, because our midterm we only cover module 1, module 2. We didn't, module 3 questions included in the quiz questions. Quiz question we have module 3 questions, but computation questions we do not have. So we can call it, we cover 2.5 modules, okay? Total we have 5 modules. So midterm we cover 2.5 modules. The remaining 2.5 modules, for the final. So not comprehensive, okay? Everything covered for the midterm, so you won't have them for the final, okay? So final, we only the new materials after midterm. But I look at the materials after midterms, we have a lot of materials. We have second half of the Laplace transform. Differentiation, integration, we haven't practiced. So that part belongs to the, homework assignment number 3 and also in the final. Then, higher order ODE. So we also need to do practice and final. And this topic, solving linear systems of ODEs. There, another small topic, series solutions of ODEs included in the final. And then there is a big topic, Fourier analysis, big module 5, big topic, must be in the final. So you can see a lot of materials in the final. All right, 8.1, basics of linear systems of ODEs. This part, based on my experience last semester, most of the students, they were not quite familiar with the linear algebra because we need to use linear algebra, okay? Although we do not use much, okay? We just use some basic knowledge, properties of linear algebra, very basic, but based on my experience, a lot of concepts, how to understand, All right, so first part I need to review, okay, the basics of linear algebra, All right. The standard form of linear system of ODE. All right. From algebraic linear system to differential linear system. So you're familiar. So linear algebra, we studied the algebraic linear system. But now we need to work on the differential linear system. But they're closely related. When we consider the characteristic equation, characteristic equation, so then we need to solve algebraic equation. All right, so we have that experience before, All right, here the situation is quite similar, All right, this is a typical algebraic equation, okay, and we can write it in a matrix form. Then, much easier to write, right? So, coefficient matrix, A coefficient matrix, then a vector variable, this X, this time, you can, when you see the boldface, we mean it's a vector, okay? Boldface, capital matrix, okay? Capital, we represent matrices. Lower cases, but boldface lower cases, so vector, a convention. So that's our convention, okay? All right. Then this B vector is a constant vector. X vector, it's a variable vector. So this notation. Then, matrix A, so it's an n by n matrix. So the n rows, n columns, and we use the subscripts. This time we use two subscripts for each matrix entry. Two subscripts. The first subscript represents the row number. Okay, row number. Row 1, row 2, row 3, row n. So row number. Okay. The second subscript, column number. Column 1, column 2, and so on. Okay, yeah. Just review a little bit. Okay, yeah. All right. So then the x vector, yeah, yeah. N components, yeah. B vector, yeah. Components, yeah. All right, yeah. Then let's compare it with the differential linear system. Yeah. All right. Left-hand side, yeah. y1 prime, y2 prime, yeah. So, n different function, n unknown functions. Yeah. So y1, y2, there are n unknown functions we need to find. Okay. Yeah. And the right-hand side, the coefficient, little a function, the coefficient, yeah, known functions. Okay. Yeah. Known functions. Then there is another. Consider the g. Yeah. G term, the last term, the g term. Another known function. Okay? Yeah. So that's the structure of the differential linear system. Yeah. All right. But we can also write it in the matrix form. Yeah. Y prime, both of its y prime, yeah, it's a vector. Yeah. So it's a derivative of a vector. Yeah. So this one, this expression, that's the derivative of a vector. Then we just take the derivative component-wise derivatives. So each component we take derivative. So it's a derivative of a vector. Yeah. Equals matrix A times vector y plus g vector. Yeah. G vector. Okay? Yeah? All right. So y prime, yeah. Y vector, g vector. Yeah. Yeah. All right. Yeah. So that's the notation. Yeah. All right. Then with that, so let's study this problem. Free motions of mass spring damped system. Free motion, yeah, yeah, free motion, yeah. No driving force, right? Yeah, free motion, not a forced motion. Forced motion, we have external driving force. Free motion, no external driving force. Yeah. Damped system, here, the damped system, so you have a, middle term, second order ODE, y prime term non-zero. The coefficient of y prime term non-zero. Yeah. So we call that coefficient a damped coefficient. Damping coefficient. Non-zero damping coefficient. Yeah. So see, this little c is the damping coefficient. Okay? Yeah. Yeah. So damped system. Yeah. Yeah. All right. Homogeneous second order ODE. Yeah. M y prime plus c y prime plus ky equals 0. All right. Yeah. Yeah. Then we use this simple example. We want to convert it to. Yeah, we know how to solve it, right? Yeah. So here, why we use this example? So you may ask, we have learned how to solve this system before, yeah, in our module 2. Yeah. We found the solution in module 2. But why we use here? So here we use this simple example to help us make a connection. Yeah. Because this time we want to use the linear system, yeah, matrix form, to find a solution. Yeah. And then we compare with our old solution. Our old solution, characteristic equation, two roots, then we write solution. Yeah. Here we use a different way, yeah, the matrix way to find a solution. Then we compare, yeah, yeah, to help us understand. Yeah. All right. Conversion, the first step, we need to convert it to a linear system, differential linear system. Okay, yeah? We have the standard way. We need, here you only have one function, y function, right? But to convert to a linear system, we need to make two unknown functions. y1 function, same as y. y2 function, y prime. Yeah. Y prime will make a second function. Yeah. All right. Yeah. Remember, in our conversion, we convert this general higher order ODE. Yeah. In that one, here second order. Yeah. The first step, we write it as y double prime, the standard form. Yeah. Then we introduce new variable, new function. Yeah, here, not variable. New function, y1, y2. Okay. Yeah, all right. y1, same as y, okay? y2, y prime. Yeah. All right. Then y2, then you can write your first equation. y1 prime equals y2. That's one equation. Okay? Yeah. All right. The second equation is this one. So the first equation, y1 prime equals y2. Yeah. The second, yeah. Now, the second one, you bring down the order of the ODE. Yeah. From second order to first order. Yeah. Y double prime becomes y2 prime. Yeah. It's a first order term. Yeah. So then the remaining, the right hand side, you can see, right hand side, there is no derivatives at the right hand side. Yeah. So we put all the derivative terms at the left hand side. All right, yeah, it's a simple conversion. Yeah. After this conversion, we can write it in a matrix format, right? Yeah, 2 by 2 matrix. Yeah. Vector, yeah. All right, yeah. So it's y prime equals ay plus g. Yeah. Y prime, y1 prime, y2 prime. Vector, y vector, a. This is a matrix. Yeah. G. Zero vector, right? Yeah. G, we don't have that G vector. G vector is a zero vector. Yeah. So we can have a homogeneous linear equation. Yeah. Yeah. Homogeneous linear equation. All right. Yeah. G equals 0. Yeah. Then the matrix format of this equation, y prime equals a matrix times y vector. So we need to solve this linear ODE. Okay? Yeah. Using our linear algebra method. Yeah. Now you can see, yeah? If you want to ask the question, why people make this kind of conversion? Yeah. The answer is very simple. Because we know in linear algebra, we have many powerful tools. Yeah. Matrix. Related to matrix, there are many properties related to matrix. Matrix decomposition, a lot of methods related to matrices. So we can apply many powerful tools in linear algebra to help us solve ODEs. Yeah. Yeah. So that's the reason, most important reason we make this conversion. Okay? Yeah. All right, then characteristic equation. We also have characteristic equation for this linear ODE system. All right, that E, that E function, yeah. But this time, yeah, the E function, we need to, yeah, using the matrix vector format. All right. Now let's recall this as our old characteristic equation like this. Yeah. How to see it from the linear system? Yeah. In our linear system, then we want to explore if we have the similar way to help us find the solution. Yeah. All right. Yeah, because based on this characteristic equation, yeah, we can get a solution easily. Y1, Y2. Oh, right? Yeah. So here, yeah, because in here, our y2 is the derivative of y1, right? Yeah. So we take derivative of y1. So y1 is e to the lambda x, but y2 in our current notation, it is the derivative of y1. So it should be lambda times e to the lambda x. Here we try to understand, okay? We try to make connection. Yeah. All right. Then, if we write a y vector, the specific form of the y vector is like this. Okay? Yeah. All right. Yeah. Then, we want to take derivative, right? Yeah. Y prime derivative, yeah. So after derivative, you multiply another lambda. Okay? Yeah. Derivative. Then you want to plug in, okay? Yeah, into that equation. Yeah. So let's continue. So A, yeah, this is our A matrix. Okay. All right. Now you can see if we plug in into, yeah, so here, yeah, let's go back. Okay. If you compare y vector and y prime vector, can you see y prime vector is just a scalar multiplication because this lambda is a scalar number. Yeah, scalar number, okay? So y prime equals lambda times y vector, right? Yeah, you can see it easily. All right. Then let's go back to the original equation. Yeah, original equation tells us y prime equals capital A matrix times y vector. Yeah, all right. So here, let's review the basic properties of linear algebra. Yeah. Scalar multiplication of a vector. Yeah. That's easy, right? Scalar multiplication, lambda. Okay, all right. So A scalar multiply vector, yeah, same as, so each component you do multiplication. So that's scalar multiplication. Okay, all right. So now y prime equals A times y. Then, yeah, because we compare these two equations. Yeah. So we replace y prime by lambda y. So we get this new equation. In this new equation, it's an algebraic equation, no derivative, right? Here you can see, yeah. After this substitution, you see we convert a differential linear system to an algebraic linear system. No derivatives. Yeah. Then it's much easier. We know how to solve algebraic linear system in linear algebra. Yeah. So here we can apply our knowledge in linear algebra to solve this linear system. Yeah. So next question, how to solve it? Okay. How to solve it? Yeah. For the linear system, you cannot use your way to solve scalar algebra equation. Yeah. So what you are familiar with, that's the scalar algebra operations. But here we have matrix, vector, algebraic operations. So a lot of things quite different. Yeah. All right, so let's continue. All right. Let's write it this way. Yeah. This equation, capital A matrix times y vector minus lambda y equals 0. Yeah? All right. Then, can we do factorization? Yeah? Here, you see the y vector, each term contains a y vector. So the question, because the common factor, even for the vector multiplication, yeah, we want to factor out the common factor, the y common factor out. Okay? Yeah? Yeah. All right. But when you factor that y out, you should be very careful. Okay? Yeah. Here, let me. Yeah. Here we review the basic knowledge of linear algebra. Okay? Yeah. Very basic knowledge. Yeah. Do not do it in a straightforward way like this. Yeah. So here, I just write here. It's hard for me to write capital, boldface. So I just write. Yeah, I can write capital, but not boldface. Yeah. Yeah. Y equals 0. Okay. If you do factorization like this, yeah, you should be very careful. Okay. Yeah. You should be very careful because A is a 2 by 2 matrix. Lambda is a scalar. How can you use a matrix minus a scalar, right? So when you do factorization, make sure you do, because the subtraction must be compatible. Okay, yeah. You need to multiply identity matrix, I2. Okay, so yeah, because here in the original equation you do not see I2, right? Yeah. But when you do the factorization, make sure your scalar you need to multiply 2 by 2 identity matrix. You know identity matrix, right? Yeah. Here 2. 1 0 0 1 identity matrix. Yeah. Then A minus lambda I2, then it's compatible. Okay? Yeah. Same matrix size, 2 by 2 matrix size. Yeah. All right. Then 2 by 2 identity matrix here. We need to use I2. Okay. All right. So multiplication of identity matrix and a vector. Yeah. The basic property. I times any vector. It does not change that vector. The same. Yeah. That's why we call it identity matrix. Okay. All right. So then here, yeah. Yeah. We review matrix multiplication. 2 by 2 matrix multiply a vector. Yeah. You know, that's the definition. Yeah. Here we review. All right. So then, yeah. So that's the reason. It explains. So lambda times scalar times y vector. Yeah. In order to do factorization, we want to write this form. Okay. This form. That y2, because then we can do the factorization. Yeah. Factor that y out. All right. There. So that's the, equation before the factorization. Then after factorization, we get this equation. Yeah. The question. Yeah. That equation. Yeah. It's a homogeneous equation. The right hand side is a 0 vector. Okay. So the boldface 0, yeah, it's a 0 vector. Yeah. Left hand side, inside the parenthesis, it's a 2 by 2 matrix. Yeah. And the coefficient is known. Okay. A, we know this is A matrix. Then lambda times I2, yeah. So that coefficient is known. Yeah. Then a 2 by 2 matrix multiply y vector equals 0. All right? Yeah. Okay? Yeah. And we know this equation must be true. Yeah. This equation must be true. All right? Then for what lambda, the question, what is the lambda? Lambda undetermined, right? Yeah, yeah. Because here, this lambda, undetermined. We need to find the lambda. Yeah. Lambda is unknown. Yeah. Variable, it's a variable, unknown variable. Okay? Yeah. Because if we can determine the lambda, then the solution, we can find the solution. Okay? All right, so the question, so this linear system, this question, for what lambda, yeah, look at this equation. Because for arbitrary lambda, this equation may not be true. That equation may not be true for arbitrary lambda, right? Yeah. Only for some very special lambda, that equation, there is a chance to make that equation true. Yeah. For arbitrary lambda, most of the time, that equation, yeah, here, I want to say this because this is a homogeneous equation. We want to solve this equation for y vector. Yeah. For most of the time, this linear equation only has zero solution because y equals 0 is always a solution, right? Y equals 0. No matter for what lambda here, it's always a solution of the equation. So we call it trivial solution, okay? Y equals 0, it is a solution, but we call it a trivial solution. Yeah. Trivial solution, because most of the time we're not interested in the trivial solution, okay? Yeah. So we're only interested in the non-trivial solution. Non-trivial solution, okay? So our goal, we want to make this linear system to have non-trivial solution. All right? Yeah. Yeah. So the question becomes, for which lambda this linear system has non-trivial solution? That's the question. Yeah. Yeah. Most of the time, this linear system only has the trivial solution. Yeah. Only for some special cases, this linear system has non-trivial solution. Yeah. So we want to find those special cases. Yeah. All right, so that's the understanding. So we continue. Yeah. All right. Then we need to apply linear algebra result, a very important linear algebra result. For a homogeneous linear system to have non-trivial solution, okay? Yeah. So here, let me describe the condition. Then I'll give you the result. The condition. Yeah. First, we have a homogeneous linear system. Okay? Yeah. Second, the coefficient matrix is a square matrix. Now, number of rows, columns, same number of rows and columns. Yeah, because in linear system, sometimes we may have a non-square coefficient matrix. Number of rows, number of columns could be rectangular matrix. Different. Yeah. Yeah. So for rectangular matrix, that linear system, then solution structure much harder. Yeah. Although we can also find it out. Yeah. But much harder. Yeah. But here we have a square matrix. Yeah. The solution structure much easier. Okay? Yeah. All right. Because the coefficient matrix is a square matrix, then the determinant is well defined, right? Yeah. Because if the coefficient matrix is a rectangular, non-square rectangular, then you cannot define determinant, right? Determinant is only defined for square matrices. Okay? Non-square rectangular matrix, you cannot define determinant. Okay? Yeah. So then we can calculate the determinant of the coefficient, 2 by 2 coefficient matrix. And there is a result, a very important result in linear algebra. Yeah. So this time, let me give you that result. Yeah, we apply that result here. Okay, all right. For a homogeneous linear system with square coefficient matrix. Yeah. So that's the, conditions. Yeah. For this linear system to have a non-trivial solution, in order to have non-trivial solution, if and only if, right, the determinant of the coefficient matrix must be 0. That result. If the determinant is non-zero, then this linear system only has trivial solution. Can you see that? Yeah. So this result, actually, it's very easy to see. Very easy to see. Okay, let me give you the result first. Then I explain how to see it. Very easy to see it. Okay, all right. All right, let me repeat another time. Okay, for a homogeneous, this result not necessarily 2 by 2. Okay, so any n by n linear system, we also have this result. Okay, all right. But all right, given a homogeneous linear system with square coefficient matrix, okay, square coefficient, then this linear system has a non-trivial solution if and only if its determinant, the determinant of the coefficient matrix equals 0. That's the result. All right. Here we apply that result. Okay? Because we want to have a non-trivial solution here. Okay? Then the condition, in order to have non-trivial solution, this determinant must be 0. Then I explain why. Okay? How to see it? Why? Then, because we use the contrapositive method to see why. Okay? Contrapositive, so if the determinant is not equal to 0, what do we have? If the determinant is not equal to 0, based on in a linear algebra, the coefficient matrix is invertible. Invertible. Here, that concept, invertible matrix. What's the invertible matrix? You can find the inverse. Its inverse, it exists. Okay? If the determinant is equal to 0, then that matrix is not invertible. Okay? You cannot find its inverse. Its inverse does not exist. Here, if we use contrapositive method, if the determinant is non-zero, then the coefficient matrix is invertible. Can we multiply inverse both sides? Yeah, we can multiply. It has an inverse. Okay, we multiply inverse both sides. The left-hand side we have y vector. Right-hand side inverse multiply 0, also 0. Then you have y vector equals 0. It's a trivial solution. Okay, if it's invertible, you only have trivial solution. You cannot have non-trivial solution. So that's why we require that matrix coefficient matrix cannot be invertible. If it cannot be invertible, then its determinant must be 0. Okay? So that's how we see. Why this condition? The determinant must be 0. Because we do not allow it to be 0. Okay? We do not allow the coefficient matrix to be invertible. If it's invertible, we multiply inverse, then y equals 0. It's a trivial solution. You only have trivial solution. You cannot have non-trivial solution. So that's not what we want. We want a non-trivial solution. Then it's interesting, it's useful. Trivial solution, it is not useful. Okay, not useful. All right, So that's the, review. Okay, the linear algebra knowledge. Try to refresh your memory. All right, let's continue this kind of understanding. Yeah. All right. Now, this time, based on our analysis, in order to find a non-trivial solution, we require, so this linear system, non-trivial solution, we require its determinant equals 0. Next thing, we need to calculate the determinant, right? Yeah. So it's a 2 by 2 matrix. So its determinant is very easy to calculate. Okay, let's do it. Yeah. Let's calculate that determinant. Okay. All right. So here, review basic property of linear algebra. Yeah. Yeah. Homogeneous linear system with a non-trivial solution. Yeah. The result. Yeah. I explained. Yeah. Yeah. So here we consider this homogeneous linear system. Yeah. But here, I should put this, square matrix. Yeah. Otherwise, this A must be a square matrix. Otherwise, you cannot calculate determinant, right? Its determinant is not defined. Yeah. So we require that A matrix must be a square matrix. Yeah. So if and only if the determinant equals 0. Yeah. So, yeah. All right. Yeah. So that's the result we use. Yeah. All right. Yeah. Yeah. Because here we need a non-trivial solution. So this is a non-trivial solution. Okay. All right. So if determinant is not equal to 0, then A is invertible. Yeah. Okay. In the linear algebra, we can find its inverse. Yeah. Yeah. But some of you may ask me, let me explain this statement. Okay. Let me explain this statement. Yeah. As our review. Okay. If some of you ask me why, if the determinant of this A matrix is not equal to 0, then A is invertible. Yeah, that's easy. If the determinant is not 0, because we have a formula to calculate its inverse. And in that formula, this determinant is at the denominator. The determinant, this determinant appears in the denominator of that formula. If it's 0, you cannot put a 0 at the denominator. Okay? If it's non-zero, because we plug it into that formula, we can find its inverse explicitly. There is a formula. Okay? Yeah. Yeah. So that's why, if it's not 0, we say this matrix is invertible. We find its inverse. It can be calculated by formula. Okay? Yeah. All right. Then, if A is invertible, then only trivial solution. You have, this equation, you only have the trivial solution. Because we can multiply inverse both sides. Okay, yeah. Only trivial solution. All right, so that's review. All right. Then, if A is invertible, then A inverse exists. And that's the basic property. Okay, matrix multiplication A times A inverse equals the identity matrix, and A inverse times A matrix also identity matrix. Yeah. So that's the basic property of matrix inverse. Yeah. All right. Yeah. So that's our review. Yeah, another special property in linear algebra, in general, for matrix multiplication, A times B, in general, not equal to B times A. Yeah, that's different from our, scalar algebra. So here, what we are doing here is matrix algebra. Matrix have many properties are different from our scalar algebra. Okay, our scalar algebra, A times B always equals to B times A. So we call the commutativity, commutable. Okay, yeah. The matrix, the scalar product is commutable. Yeah, but matrix product in general is not commutable. Okay? Yeah. Only in special cases, in some special cases, the matrix product can be commutable. Yeah. So here I mentioned that. In general, not commutable. Okay, all right. Then we need to calculate the determinant. Okay. Yeah. After we finish this slide, so we complete the class today. Yeah. So let's just calculate the determinant. All right. Yeah. Then A minus lambda times identity, 2 by 2 identity, I2, 2 by 2. Yeah. So we get a 2 by 2 matrix. Yeah. The lambda only appears in the diagonal entries. See? Yeah. Lambda only appear in the diagonal entries. And the determinant, we have determinant formula, right? Yeah, 2 by 2 determinant formula. You know, so yeah. Here, let's review 2 by 2 determinant formula. A, B, C, D, this matrix. Okay, if we calculate determinant, so usually determinant we use this notation, the vertical bar. Okay, yeah, equals A times D minus B times C. Okay, yeah, that's the 2 by 2 determinant formula. Right. Yeah, here we can do that formula. Okay, yeah, yeah. The diagonal, the product of the two entries in the diagonal, negative sign, yeah, and minus that one. After simplification, you can see its determinant equals our original characteristic equation, right? You can see that's the connection. Yeah, yeah, yeah. Before we use the linear algebra approach, yeah, we know that lambda squared plus c over m lambda plus k over m equals 0. That's the characteristic equation of that damped free motion system. Yeah, that's the characteristic equation. Now we calculate the determinant of the coefficient matrix. That determinant is the same as the old characteristic equation. Yeah. Then we solve the characteristic equation. We find the lambda value. Yeah. So we can get a solution. But here, after you solve this equation, you find the lambda value, you get the vector solution like this, right? Lambda 1, lambda 2. You have two solutions. Yeah. That means you have two vector solutions, y1 solution, and a y2 solution. Yeah. y1 corresponds to lambda 1, y2 corresponds to lambda 2. So you have two vector solutions. Okay? Two vector solutions, yeah? If you put two vector solutions together, you form a basis, yeah? Basis concept. Basis of all the solutions. Yeah, here, the basis of all the solutions. Yeah. All right, yeah? So the basis is important. The basis, yeah? In our second order ODE, we also have y1, y2. We get a basis, right? Yeah. Wronskian. Yeah. Here you can see, here actually we put these two solutions together. You get the matrix corresponding to that Wronskian, right? Wronskian is a determinant. But determinant of that matrix, what matrix? y1, y2 together. Okay? Put the y1, y2 together. Yeah? Because each y1, that one, yeah, actually, oh, sorry. The y1, y2 I use here, you get confused because we have this little y1, y2, right? Yeah. That's why later people use the capital letters. Yeah, because lowercase, you get a confusion. Okay? So later, so people use that, capital Y1, capital Y2. Yeah. As the solution, solution vector. It's not a matrix. So here, although the capital, but Yeah, yeah. Sometimes the, symbols. It's very hard to choose good symbols. Yeah. Yeah. Sometimes, yeah, because if sometimes people use, this vector. So you try to separate. Okay. Yeah. Y to this, that vector. Otherwise, it's hard to separate different notation. Yeah, because capital Y later people want to use that form the matrix containing all the solutions. That's the capital Y. Yeah. So you don't want to get confused. Yeah. Anyway, yeah. So let's stop right here. Yeah. So we just review some linear algebra basics.